Hello, everyone. Today we have Foster Tom from Europe, Berkeley, right now, used to be Berkeley, who'll be talking about a combinatorial Schur expansion of triangle-free horizontal strip LLT polynomials.
Great, thank you, Ram, and thank you for inviting me. I'm really happy to be here to tell you about this work on the Schur expansion of certain LLT polynomials that I've been working on quite a lot last year. Before I start, I'm just going to say my internet isn't so good, so if I happen to freeze or disappear, then that would be the reason. And I'll also say I'll be keeping an eye on the chat, so feel free to just type any questions, or if you prefer to just interrupt me, feel free to just do that, and I'll address your questions. So yeah, I wanted to tell you about LLT polynomials. So LLT polynomials were originally defined by these three authors, Lascaux, Leclerc, and Thibon, in terms of ribbon tableau. But Hagelin, Tayman, Lower, Rummel, and Ulyanov gave an alternative definition in terms of tuples of skew diagrams, and that's the one I'm going to work with today. So let me just begin by defining LLT polynomials in this way, and then I'll start talking about some questions we can ask. And to make things a bit easier, I'm going to focus on what I call the horizontal strip case, where each skew shape is a row. There's still plenty of difficult questions in this case. So if I have a tuple of skew diagrams, each of which is a row, I'm going to define the horizontal strip LLT polynomial to be a generating function over tuples of semi-standard Young tableau, where I keep track of this statistic called inversions. So an inversion is going to be either a pair of cells in the same column with the bigger one below the smaller one. So the entry in the lower cell is larger than the entry in the cell above. Or it's going to be a pair of cells in adjacent columns, where the bigger entry is above and exactly one column to the left of the smaller entry. So an inversion is going to be a pair of cells that are either arranged like this or like this. Okay, so let's look at an example. So on the left here, I have a tuple of skew diagrams, each of which is a row. To calculate the LLT polynomial, we write down all of the semi-standard Young tableau of this shape. So that just means I fill the cells with positive integers, weakly increasing from left to right. There are many, many ways to do this, so I've just written two of them out for us here. And then for each one, what I do is I find the inversions. So hopefully we can still see it here. An inversion is if I have a bigger number below a smaller number in the same column. So T has 4 inversions of that sort. And an inversion is also a bigger entry above and exactly one cell to the left of a smaller entry. So there's also an inversion of that type here. So this tableau T contributes this monomial. So Q to the number of inversions, and then a monomial that keeps track of the entries of the tableau. So I've got a bunch of other terms, and then I've got a Q to the 5. I've got 3 1s, 2 2s, and 4 3s in this tableau. So T contributes this monomial to the LLT polynomial. And similarly, I've got just another example U here. So if I do the same thing, I have inversions whenever I have a bigger entry directly below a smaller entry, or when I have a bigger entry above and exactly one cell to the left of a smaller entry. So I've got, I think I should have 3 inversions in this example. So the tableau U contributes this monomial to the LLT polynomial. So I'm going to have tons and tons of terms like this. And this happens to be a symmetric function. I've written out the Schur expansion of the LLT polynomial in this case, just so we can see an example of what the whole thing looks like. So are there any questions about the definition, about inversions, or any of this up until now?
Nope, all good.
Okay, great. So Lascaux, Leclerc, and Thibon, they defined LLT polynomials in a slightly different way originally, but they showed that what they defined was a symmetric function. And 10 years later, Gronowski and Heyman showed that LLT polynomials are in fact Schur positive, meaning that if you write it in the basis of Schur functions, as I've done here, the coefficients are all polynomials with positive coefficients. Gronowski and Heyman used Kazhdan-Lustig theory. They showed that the coefficients are values of certain Kazhdan-Lustig polynomials. And it's a major open problem to find a combinatorial interpretation for these coefficients. I'm just going to mention some applications of LLT polynomials to some areas of algebraic combinatorics you might be familiar with. If you haven't seen them before, then don't worry so much, it won't really come up. I just wanted to mention some ways that are related to some other things. So Carlson and Mellett proved the shuffle conjecture recently. The shuffle conjecture gives a combinatorial formula for this quantity nabla of En. So nabla of En is the Frobenius series for the space of diagonal harmonics. If you've heard of the n+1 to the n-1 conjecture, Heyman proved that that space has that dimension. But the shuffle conjecture gives a combinatorial formula in terms of dig paths. So if we have a dig path, next to every north step, we just draw a box like this. And then a Rord-Perkin function means that we need to put positive integers in these boxes, strictly increasing from bottom to top. And there's some statistic called diagonal inversions. But essentially, the way that diagonal inversions have been defined makes it so that this generating function here is exactly an LLT polynomial indexed by columns. So really, this shuffle conjecture is a combinatorial formula in terms of LLT polynomials. This is one way that we could interpret it. The other application that I want to touch upon is Mcdonald polynomials. So if I have a partition mu of n, this V of mu is called a Garcia-Heyman module, and it's just a span of partial derivatives of sort of a generalization of the Vandermonde determinant. If you've heard of the n factorial conjecture, Heyman proved that this space has dimension n factorial. And then the Mcdonald polynomial is the Frobenius series of the Garcia-Heyman module. Haglund, Heyman, and Lower found a combinatorial formula for the monomial expansion of Mcdonald polynomials, but they found that it actually implies an expansion, a positive expansion in terms of LLT polynomials, where each of the shapes is a ribbon. So I won't go into this too much, but just for an example, if mu is the partition 3, 2, they have an expansion in terms of LLT polynomials, and the number of terms is the number of subsets of just the part of just the cells of the partition that are not on the first row. So Haglund, Heyman, and Lower found that Mcdonald polynomials expand positively into LLT polynomials. And because it's known that LLT polynomials are Schur positive, this gives us a proof that Mcdonald polynomials are Schur positive. But once again, having a combinatorial formula is still a very wide open question. So what I'd like to do is maybe describe some of the results in terms of finding a combinatorial Schur expansion. So Gronowski and Heyman showed that if I have a shape that looks sort of like this, where all of the rows are left justified like this, then the LLT polynomial actually coincides with something called a Hall-Littlewood polynomial, for which Lascaux and Schutz and Berger found a beautiful combinatorial formula for the Schur expansion in terms of a statistic called cocharge. So I've written out here properties that can be used to define cocharge. It might not be the classical definition you might be familiar with. I'm not really going to go into this too much. I'm just leaving this here in case anyone's interested in reading a way to define cocharge. But I guess what I really wanted to take away is that cocharge is just some number associated to Tableau, and it's sort of bigger if you have a lot of entries on top of other entries. So just one example to illustrate what I mean by that. If I have a Tableau that has only two different entries, so only i's and j's, then the cocharge of the Tableau is just the number of entries on the second row. So the more that you have entries on top of others, the bigger the cocharge is. And just to give a bit more of an example of this, if I have this tuple of rows on the left, so these are sort of left justified, then if I want to calculate the coefficient of, for example, S621, then I'm going to write down all of the Tableau with shape 621 and of weight 432, which are these row lengths here. So there are two such Tableau. We've got S and T here. And we calculate the cocharge, and this gives us the coefficient of S621. So the way that I'm seeing things is that the problem I want to address is to find a generalization of cocharge that will give me a combinatorial Schur expansion of an LLT polynomial, even when the rows don't sort of look like this. So if the rows are just arranged in some random fashion, can I find some sort of set of Tableau and some sort of variation of cocharge that will give me the combinatorial Schur positive expansion? And I just wanted to present one result that some people have done that's kind of in the same flavor of what I would like to do. So if my tuple of rows is unicellular, which means that each row, each skew diagram consists of exactly one box, then we can associate a Dick path and a certain kind of graph to that shape. And these authors, He, Nam, and Yu, showed that if the graph takes on a certain form, then the LLT polynomial is given by this Schur expansion, where they define some statistic here. So I'll just sort of show you in an example what their theorem looks like. So I know there's a lot here, but I'll go through it slowly. If I have this tuple of rows on the left here, this is unicellular, so every skew diagram is a single box. I'm going to read the entries in this way, so from bottom to top and from left to right. So this is 1, 2, 3, and 4. I can now draw a graph where the vertices are the boxes and where two vertices are adjacent if it's possible to form an inversion between cells in these boxes. So just recall inversions happen if I have two cells in the same column, or if I have a cell above and to the left of another cell. So I've got these four edges here, and I have this graph gamma. I can form a Dick path from this by just reading the edges. So I've got 1, 2, 1, 3, 2, 3, and 3, 4. And then I just draw this Dick path by going just above those cells. This A here is called the area vector of the Dick path. It just means I look at the number of full boxes in between the Dick path and the diagonal in each row. So here I've got one box and then two boxes in one box. And this theorem of He, Nam, and Yu says that if this graph is a melting lollipop, so I think it's so cute, a lollipop is sort of a complete graph and then a path coming off of it. And a melting lollipop is where we can remove some of these edges if we like. So this example gamma here is indeed a lollipop. So they showed that if my graph is a melting lollipop, then if I want to calculate the Schur expansion, if I want to calculate the coefficient of S22, for example, I write down all of the standard Young Tableau of this shape. So I've got S and T here. I look at the descent sets of these tableaux, and I sum the corresponding indices of the area function. So for S, only 2 is a descent. So I is a descent if I plus 1 appears above I. And so I just take A2, which is 2. And then for T, 1 and 3 are descents. So I take A1 and A3, and I get 2. And their theorem tells me that that's how I can find the coefficient of a Schur function in this LLT polynomial. So this is very much the sort of thing I would like to do. If my rows are arranged in a certain way, I want to define some sort of set of tableau and some sort of statistic that'll give me a combinatorial Schur positive expansion. Are there any questions up until this point?
Doesn't look like it.
Okay, so now I'm going to get into a little bit about how I was approaching this problem. So one thing that you begin to notice when you're just playing around and putting numbers in the boxes is that if you've got a configuration that looks like either of these, the cell X can make an inversion with Y or with Z. So an inversion happens if an inversion can happen if I have 2 cells in the same column or if they're in adjacent columns. However, X cannot make an inversion with both of them, because to make an inversion with Y, we would have Y bigger than X. And if X makes an inversion with Z, then X would have to be bigger than Z. However, since Y is to the left of Z, the rows need to be weakly increasing. So any cell makes at most one inversion with the cells in some fixed row. So if I fix a cell and I fix a row, there's at most one inversion between a cell and a cell from that row. And it made me think that I wanted to examine this idea of the maximum number of inversions some more. If I have rows R and R prime arranged like this on the left, the maximum number of inversions I could get would be doing something like this. So I need to match up the cells, and because no cell can occur in more than one inversion, this is the most that I can get. On the right, because we can have inversions between adjacent columns, it's possible to get 3 inversions, but that's the maximum number of inversions I can get between these 2 rows. So I define this integer m of r prime to just be the maximum number of inversions I can get between rows r and r prime. I've sort of written out the definition properly here. Essentially, I'm just saying how much do these rows overlap. So these 2 rows overlap in 2 places. But if you start to the left, I sort of want to shift 1 space to the left and see how much they overlap. But really what I'm doing is trying to look at the maximum number of inversions I can make, because this will tell me, the maximum power of Q that will arise in the LLT polynomial. And then what I wanted to do was generalize this unit interval graph of H, Nam, and U a little bit more to the case where I have tuples of rows. So if I have a tuple of rows, what I want to do is define a weighted graph. And the weights will keep track of the maximum number of inversions I can make. So once again, I'll just sort of show you with an example. If I have this tuple of rows here on the left, I'm going to look at the rightmost cell in each row, and I'm just going to read them in the same order as before. So bottom to top, left to right. So this will be 1, 2, and 3. I'm going to draw a graph where I have 3 vertices. Each vertex corresponds to one of these rows. So I've got V1 that corresponds to this row, V2 that corresponds to that, and V3 that corresponds to that row. I'm going to say that each vertex has a weight, which will just be the number of cells in the corresponding row. So V1 has weight 2, V2 has weight 4, and V3 has weight 3. And then I'm going to draw edges if I can make an inversion between cells in the corresponding rows. and I'm going to weight the edge by the maximum number of inversions I can make. So this is where this integer is showing up. Between v1 and v2, I can get 2 inversions. So that gives me this 2 here. Between v1 and v3, I can get 1 inversion between these rows, so that's this 1. And then finally with v2 and v3, I can have 2 inversions. So this is how I define a weighted graph corresponding to this tuple of rows. This is an idea I had where I wanted to generalize the graph from the unicellular case. And then my main theorem states that if this graph happens to have no triangles, so I guess it doesn't apply in this case because it's a triangle. If the graph has no triangles, then I define a statistic that I call cocharge pi, and it really gives me a combinatorial Schur expansion of the LLT polynomial. Okay, cool. So how did I approach this? There is this notion that was defined by another student of Heyman's named Chris Miller. If we have two tuples of skew diagrams, we say that they are LLT equivalent if they have the same corresponding LLT polynomial. And in fact, moreover, if I can append any collection onto both of them, and they'll still have the same LLT polynomial. I think Miller was looking into when LLT polynomials were equal, and he noticed this stability phenomenon occurring quite a lot. More generally, if I have a formal linear combination of shapes, we can ask the same question whether the corresponding combination of LLT polynomials is equal, even if we append a fixed collection onto all of the shapes. So this might look a bit confusing, but I'll demonstrate what this looks like in this example. If I have a row like this, and I just break it up at some point, I claim that I have this LLT equivalence of these shapes. So what does this look like? If I wanted to prove that q times this LLT polynomial plus this LLT polynomial equaled this combination of LLT polynomials, the most direct way to do it would be just to have a bijection between tableaux that are either of this shape or this shape, and tableaux that are either of this shape or this shape. And it needs to preserve weight and do the right thing, do inversions. And indeed, it wasn't too difficult to find such a bijection. There are a few different cases, but essentially I can get a bijection between tableau of either of these two shapes and tableau of either of these two shapes. The only thing I'll mention is here I have one inversion, and then that sort of balances with the q here. So I just need to check that this kind of thing works. When it comes to LLT equivalence, I actually promised something a bit more, that I can append any collection of shapes that I want, and the combinations are still equal. But in this example, if you notice that with the bijection, I've preserved the entries along each column, what it means is that if I were to append some other shapes onto here, if I just sort of translate these entries over to here, because the entries along each column are the same, the number of extra inversions I would make would also be the same. And so a bijection like this can actually prove LLT equivalence. Just for another example, I say that two rows commute if the maximum number of inversions I can make is the same no matter which row is on top. So on the left here, I have 0 inversions. And if I move this one down here, I still have 0 inversions. On the far right, I can have 3 inversions like this. And if I were to move this row to the bottom, I could still have 3 inversions. So the pair of rows on the right commutes as well. However, in the middle, when it's like this, I can have a maximum of 2 inversions. Whereas if I switch the 2 rows, I would have a maximum of 3 inversions. So in this case, the rows do not commute. And why am I calling this commuting? Because if I have two rows that commute, I can switch the two rows and I'll get the same LLT polynomial. So even if there are a bunch of other rows, if I have two commuting rows like I do here, I can switch the two rows and the LLT polynomial will be the same. This is proven by a bijection similar to before. And then by combining the two results, I get this other one that if two rows do not commute, then I get some sort of linear equivalence relation that looks like this. And really, maybe I won't dwell too much into it, but what it gives me is a recurrence on LLT polynomials that I can express in terms of these weighted graphs. So I get something a bit more general like this, but for now, it'll suffice to just say if V1 has exactly one neighbor, Vj, then I can write down this linear relation in terms of the graphs of the two poles of skew diagrams. So using this recurrence is the main combinatorial tool. And then the other problem I had was, what should this notion of cocharge be that would give me a Schur expansion of the LLT polynomial? So I just looked at a few small examples of things that happened, and some interesting things showed up. So if I have a tuple of just two rows, so the graph just looks like two vertices and an edge, then the LLT polynomial actually has a pretty nice form. So I'll show you what this looks like in this example. So if I've just got something like this, the Schur functions that show up are those that show up in S5 times S3. So that would be these Schur functions. And the powers of Q just go up one at a time, 0, 1, 2, 3. Now I told you that the weight of these edges represented the maximum number of inversions I could have, the maximum power of Q that was possible. And in fact, something really nice happens. If this weight is smaller, the power of Q just goes up one each time until it hits that maximum, and then it stays there. So these are the Schur expansions in the case of these graphs here. And I've also just written the tableau of that shape and of weight 5, 3, just to look at that as well. So I guess I'll remind you that cocharge, I didn't really define it, but it's an integer and it's bigger if I have a lot of entries on top of other entries. In particular, if I have just ones and twos, cocharge is the number of twos on the second row. So we sort of see in this case the q to the 0, 1, 2, and 3. It made me think that in general, what I should do is maybe cocharge should split up as a sum over the contribution of having j's above i's. And when I have j's above i's, maybe I would get some sort of cocharge sub I comma j. And it would be limited by the weight of the edge between vi and vj. So if the weight of that edge was smaller, I just need to take the minimum between the cocharge and this number. So with this example, it made me think that maybe I should do something sort of like this. The cocharge of a tableau, I need to look at the contributions of j's being above i's. And I need to take the minimum between that number and the weight of the corresponding edge here. So in the case of paths, this turned out to be exactly the right thing to do. And it's a rather elegant story. So in a case of paths like this, I kind of want to think about the contribution to cocharge arising from twos being above ones, from threes being above twos, and so on. And the way that I could define that was, I would say that t restricted to i's and I plus ones would be, I take t, I erase all the entries aside from I and I plus one, so I get some skew tableau. I rectify it, and then I just get a tableau with two different kinds of entries. So then I'll look at the number of entries on the second row. So t restricted to i's and I plus ones would be this. And then cocharge sub I comma I plus 1 would be just the cocharge of that rectified tableau. And then combining it with this other idea that I want to take the minimum between this individual contribution to cocharge and the weight of this edge. This turned out to be the definition of cocharge sub pi in the case where my weighted graph pi was a path. And this was exactly the right thing to do to get a combinatorial Schur expansion of this LLT polynomial. So let me show you what this looks like in this example. So if I have a tuple of rows that has this graph, so this is a path. If I want to find the coefficient of S733, for example, I write down all the tableau of shape 733 and of weight 4324. So there are 3 of them here, but we can just look at this first one. So for S, what I want to do is restrict S to 1s and 2s. So I get this tableau here, S1, 2, and I just look at the number of entries on the second row. So there's 1. Then I restrict S to 2s and 3s and get some skew tableau, which I'm going to rectify. And I get this tableau that has 2 entries on the second row. And then the same thing for 3s and 4s. So I look at the 3s and 4s, I rectify, and I look at the number of entries on the second row. And in case the weight of the corresponding edge is smaller, I need to take the minimum between these 2 numbers. So even though I have 2 entries on the second row, because this weight is 1, in a sense, I'm only allowed to have 1 inversion in this case. So I take the minimum, which is 1. And when I sum these numbers, this gives me the cocharge of the tableau corresponding to this graph. So I do the same thing for these other 2 tableaux, and this gives me the coefficient of S733. So are there any questions about this example or sort of the motivation behind the definition? Okay, great. I just want to give you a quick idea of what this proof looks like because it's very combinatorial. So I hope you'll enjoy it. If I apply the recurrence that I wrote up here, so if I apply this recurrence in this example, then I'm going to get this linear relationship between the LLT polynomials for these graphs. And I guess I'll just emphasize that this 2 here became a 1, and then there's this other term where something a little different happened. If I use induction on the total weight of the edges, I just need to show this equality. And this is a very combinatorial thing. So I'm going to look at this first term. So this first sum, if I look at the coefficient of S733, it corresponds to these 3 tableaux. The power of Q in front basically tells me that I should increase the cocharge by 1 for each of these tableaux. So just in this sum, I've written the cocharge for each of the tableaux, and the power of Q tells me I should increase these numbers by 1. And then I sort of ask myself, how much does this correspond to this? You see, if I compare these 2 graphs, I've changed this 1 to a 2. And it means that instead of taking the minimum between 1 and something, I'm taking the minimum between 2 and something, which means that as long as, so if cocharge sub 1 comma 2 is at least 2, then when I take the minimum between 2 and that, it is indeed 1 more than the minimum between 1 and that number. So increasing the cocharge by 1 is exactly what I want to do in this case. However, if cocharge sub 1 comma 2 was at most 1, then increasing the power of Q was the wrong thing to do, because that term should stay the same. So I'm really viewing this equation here, I'm viewing this as sort of like a main term, and then this is going to be a correction term. So I've got these three tableaux here, S, T, and U. And for T and U, cocharge sub 1, 2 is at least 2, so increasing it by 1 was the right thing to do. But for S, I've only got 1, 2 above a 1. So I don't really want to increase the power of Q by 1, but that's where the correction term comes in, because it corresponds to just this single tableau, where it has the same cocharge, and basically what this 1 minus Q factor is doing is it turns the Q to the 5 back into a Q to the 4. So I guess what I'm saying is that for these terms, I've got a Q to the 4, so the power of 4 gets increased by 1, but then I have this correction term, which basically decreases it back to 4, and that's exactly what I want to do. Maybe just to be a bit more explicit about what's happening, I have a bijection between tableau corresponding to this graph and the tableau corresponding to the other graph, for which cocharge sub 1, 2 was at most 1. So when the cocharge was at least 2, multiplying by Q was the right thing to do, and that's great. It gives me the right terms. When the cocharge is at most 1, they sort of cancel out with this term, and the exponent does not increase by 1. And in fact, maybe in this example, you might be able to see this bijection at work. If S has cocharge 1, 2 at most 1, what I can do is there'll be 3 ones here that don't have 2's above them, and I can just change those 1's into 2's. So yeah, I fear I might not have explained it too well. Are there any questions about about what this looks like? Okay, so yeah, maybe I'll move on. So this was what happened if my graph was a path, and this seemed to me like it was definitely the right thing to do. It really fits into the story, and the definition of cocharge was really exactly what it had to be in order to make the argument work. Then I wondered how much I could generalize this, so I started with paths. I thought maybe I could think about trees. And when I'm calling these triangle-free graphs, I'm being a bit dishonest, actually, because just from the algorithm that produces these graphs, if I have no triangles, then I can't have any cycles at all, so I have to be a union of trees. And moreover, I actually have to be a union of caterpillars. So I think this is so cute. A caterpillar is a graph that's a path, and then I just have some vertices of degree 1 attached to some of the vertices of this path. So I have to have graphs that look like this. So I asked myself how I could generalize the argument in this case. I guess I have a few problems. I now have, for example, V1 adjacent to V4. So I wanted to think about what's the contribution to cocharge arising from 4s being above 1s. If I erase all the entries that are not, if I erase all the entries other than the 1s and the 4s, I no longer have a skew tableau like I did before. So there wasn't really a canonical way to rectify and get a tableau. I tried, doing jeu de terrain slides from one direction or the other, but they didn't quite work out. It turned out that what I wanted to do was just restrict to entries between 1 and 4. So I would get a skew tableau that I could rectify. But then another problem was, how exactly do I define cocharge sub 1, 4? And I tried a few plausible sounding things, but then the following thing is what ended up happening. So back when I had just 1s and 2s, I said that the cocharge was the number of entries on the second row. So in this case, it would be 5. And then I found that a really weird way to think about this number was I could ask myself, how many times can I move this bottom row to the left and have the entries, have the columns still strictly increasing from bottom to top? So I could do it 1, 2 times, but not 3, because then I'd have a 2 on top of a 2. So before we were thinking of this as 5, but a really weird way I could think about it is the number of 1s, which is 7, minus the distance that I can move left. So I can consider cocharge from this perspective, and it turned out that this was exactly the thing to generalize. So if I have some tableau, I define f of t to be basically how much I can move the bottom row to the left and still have the columns strictly increasing. So in this case, I could move the bottom row to the left 3 times. With t, it's a bit of a weird case. I have this other condition that I can only move it at most the number of smallest entry. So I only have 3 2s, so I'm only allowed to move it 3 times. But this turned out to be the right way to generalize this problem to the triangle free graphs. So t restricted to i's and j's would be, I'd restrict to entries between I and j and rectify. And then cocharge sub I comma j would be the number of i's minus the distance I could move left. So in the case where j equals I plus 1, this is just the thing we had before. And then this turned out to be the thing that worked. The proof is very much the same as it was before. And maybe I'll show you an example of what this looks like. So if I have a tuple of rows with this weighted graph, so this one isn't a path anymore. This is just more generally a caterpillar. If I want to calculate the coefficient of S733, I'll draw all the tableau of shape 733 and of weight 4153. So there are 3 of them here. If we just look at the first one, S restricted to 1s, 2s, and 3s is the interesting bit. So here's S13. I ask myself how far I can slide the bottom row to the left so that the columns are still strictly increasing. Let's see, so if I do that 1, 2 times, I'm good, but 3 times and I have a 3 on top of a 3. And then I look at the number of 1s minus the distance I can move left. So 4 minus 2 is 2. For S23 and S34, it's basically the same thing as before. I add those numbers up and I get a 5. I do the same thing for the other tableau, and this gives me the coefficient of the Schur function. Are there any questions about this example or this generalization of cocharge?
No, Nantel looks happy, but no questions, I don't think.
No, I'm just amazed by this kind of changing definition, and it works perfectly.
Yeah, thank you. I was really excited as well. I've got just a couple minutes, so I just have one remark to make at the end. So if I have my LLT polynomial indexed by a tuple of rows, I didn't actually really need to know the tuple of rows. I only really needed to know this weighted graph. So, I mean, it follows directly that if I have 2 different tuples, but they have the same weighted graph, and we're in this triangle free case, then they have the same LLT polynomial. I actually believe that really this happens in general. So whenever I have 2 tuples of rows, and the weighted graphs are they don't even need to be the same, but if they're isomorphic, so if I just relabel the vertices, they're the same, then I believe that the corresponding LLT polynomials are equal. In other words, all you need to know is just the length of the rows, and these funny integers that I've been interested in, which tell you the maximum number of inversions between different pairs of rows. And if you have this information, you'll be able to determine the horizontal strip LLT polynomial. Last year, I spent quite a while trying to prove this. I think I have a pretty good plan of how I could attack it, but ultimately, I wasn't really that happy with it, and I decided not to call it a proof. I'm just calling it a conjecture, but it's something that I want to return to at some point. The real dream, though, is if I could generalize this result to cases where it's not, to just general graphs, then I might be able to prove this conjecture directly just by looking at whatever formula I managed to come up with. Okay, so thank you very much for your time and attention. You've been a great audience, and I'm happy to take any questions and have some further discussion.
Awesome. So, sorry. Awesome. Let's thank the speaker. Are there any questions? Nantel, is that you having a question? Okay, go.
Yes, let me be visible. I was wondering your conjecture. So is it your conjecture that you just mentioned at the end? You essentially say it's a necessary condition to be LLT equivalent. Do you think it will be sufficient?
I'm sorry, I'm not quite sure I'm following.
Do you think that if they have different graphs, they will have different LLT?
Oh, yeah, this is a really good question. It's actually not true, and I'm gonna say it's not my fault that it's not true, because it's not true even in the unicellular case. So if I have
good.
If I have this, and if I have this, so even in the unicellular case, when we just have this simple unweighted unit interval graph, these graphs are different, but they have the same LLT polynomial, and actually they have the same chromatic symmetric function, and there's a relationship between the LLT polynomial and the chromatic symmetric function. So it's maybe not too surprising that I have a coincidence like this. I think it might be interesting to kind of go the other way and see what we can deduce about chromatic symmetric functions from LLT polynomials. There's sort of a plethistic relationship between an LLT polynomial and a chromatic quasi-symmetric function.
Oh, the Q quasi-symmetric function, you mean the Ershin wax, right?
Yeah, so if I have a graph, maybe the vertices are labeled 1 to n.
Yeah.
Then what is it? The Q chromatic quasi-symmetric function is I sum over proper colorings. And then I have this this statistic where number of I and j such that something like this. In fact, an LLT polynomial, if in the unicellular case, I'm just putting an entry in each box. So the LLT polynomial is the same sum, except the colorings don't need to be proper, not necessarily proper colorings. And so LLT polynomials are closely related to these Q quasi-symmetric chromatic functions.
I see.
In fact, there's an explicit relationship. I might not be able to get it right. Something where I need to put in Q and There's some kind of thing like this, maybe a power of q here, and some other things. But in fact, it implies that linear relationships between these chromatic symmetric functions are equivalent to linear relationships between LLT polynomials.
But this is only for unimodular, right?
Yeah, just the unicellular case.
Yeah, unicellular. Sorry, I always say bad words, wrong words, but yes. Okay, thanks.
Oh, yeah, thank you for the question.
Can I ask one real quick? How much has this equivalence, this LLT equivalence, been explored? Is there some sort of an idea of what kind of characterization you could do on when two LLT polynomials are equivalent whenever you append? Is there a very limited number that this happens, or does it happen for a lot?
Oh, this is a good question. My understanding is that it's not very well known. I guess LLT polynomials are sort of generalizations of products of Schur functions. And if we want to know about when products of Schur functions are equal, my understanding is that that's very, very difficult. This phenomenon is a bit stronger than just being an equality. So there are plenty of cases where the LLT polynomials are equal, but not if we append some other shapes. I was looking into it a little bit and found some necessary conditions, but I feel like in general, not too much is known.
Thanks.
Yeah, it even delves into equivalence of skew shape, which is also for Schur function, which is also, like a problem as well.
Right, yeah, this question can certainly be asked for two poles of skew diagrams in general. I guess one thing I'll mention, which is kind of interesting, so you need to have the same collection of rows here. So how should I say this? If I have, a collection of skew diagrams like this, and I'm asking whether it's equivalent to some other collection that maybe has some things like this, it's necessary that you sort of have the same collection of rows. If you took all of the skew diagrams and you split up the rows really do just need to be permuted in some way. So I've managed to find a necessary condition like that.
Cool.
Are there any other questions? Okay, seeing none, let's thank the speaker again.
Hey.
Awesome. Thank you very much, everyone.